Motors do way more than just spin. How you configure and program them can be the difference between a robot that feels smooth and responsive and one that will fight you all season. If you're a programmer willing to learn, then this video is for you. Hello, welcome back to the YAS channel, and today we're going to be learning everything you need to know about how to program a motor. I already made a video very similar to this one, but it was more about the mechanical side of motors. Some vocabulary you need to know in this video is that motors have two types, brushed and brushless. We're going to be mostly talking about brushless motors today, as this video is also catered to one of our libraries, YAMS, a easy-to-use mechanical library that will help you program your mechanisms efficiently and simply. Some other terms you want to know is the word motor controller. These could be either external or integrated. Like these here, these are external. This would be your Spark Maxes, your Spark Flexes, and they kind of control the robot. While the integrated ones, they also control the robot, or not the robot, they control the motors. These right here. Each motor controller is tied to one motor, and these can also be integrated into the motor, and they require less space compared to external motor controllers. We're going to be talking a lot about the software of how to be programming a motor, and if you want to follow along, we have some YAMS documentation you can look at. Here is to the YAMS doc, and here is to the Java docs, where it's going to be deep dive into every method that is provided by YAMS. One of YAMS' specialties is going to be this motor controller class. The YAMS motor controller class, it looks something like this. It standardizes how you program a motor. I can push this side here. Whether you have a rev loader, a CTRE, a thrifty, YAMS is able to standardize this process from different vendor libraries for you to be able to create your smart motor controllers, all your configs, your motors, all the exact same way and configure them the exact same way. Note that some configurations may have some exceptions to this rule of everything's going to be the same way because they're incompatible or they are incomplete, and you would have to have maybe add a set voltage or a set duty cycle when you're using YAMS with this type of configuration. How do I make a smart motor controller? To make a smart motor controller, you're going to need to have a vendor object, attached motor, and a smart motor controller config. Your vendor object is going to be, tied to the vendor. You can tell by here, this is Spark wrapper, you got a Talon FXS wrapper, Nova wrapper. Here we have even like a DC motor where you can tell like what type of vendor it is, kind of. And then you have your attached motor, which is going to be the motor that's attached to the smart motor controller. So this could be, you can create a Spark Max, you can create a DC motor like this, you can create a Talon net. Or how my team does our code, 3481, we create a motor object up here, and it's a Spark Max, very easy to label. And then we can go down here to our smart motor config and just put the name of our object as well as what kind of motor type it is, how many of them, and then our config, which makes our code a lot cleaner. YAMS supports all types of motor controllers. We got Spark Maxes, Spark Flexes, Thrifty Novas, Talons, and so on. If you want to create a DC motor, if you click on this link here, it's going to provide you all the information you need to know to fill out this information right here, as Recalc is a really useful website for motors and programming and mechanical in general. Well, there's 4 different ways you can control your motors via position, velocity, duty cycle, and voltage. Position is going to be how a measurement from your motor, and it's going to be either in degrees or meters. Well, not specifically degrees and meters, but It is going to be in angles and distance. Angles is going to be for anything rotational base, like arms, turrets, wrists, etc. While distance is going to be for elevators, linear actuators, etc. You also got set velocity, which is going to be how fast something is going. You can do this in meters per second, miles per hour. You can do RPM of whatever you want. And it's really simple. You do dot set velocity. You want to make sure that when you're doing these two things, you want to keep in mind that the different types of mechanisms you have, whether it's an angle, you want to use something that's based on rotation. And if you're doing distance, like set velocity here, meters per second or meters of, that needs to be for any elevators or linear actuators, otherwise it could overload. Some other things that you might want to know about is going to be set duty cycle and set voltage. Set duty cycle is going to think about it as like a constant power to your motor. It's a number ranging from 0 and 1. 0 being no power being sent to the motor, and then 1 is going to be full power. And then you also got set voltage, where you put a set amount of voltage into a mechanism motor, and you can see what it does. The smart motor controller config is going to be kind of how you tailor each motor to that mechanism. It's how you configure each smart motor controller, and not all features is going to be supported on every single smart motor controller. There's 5 different categories that you can break up your smart motor control config: your motors, closed loop, encoder, external encoder, and telemetry. Here is kind of what that looks like. You see here I have my smart motor controller config object, and in here I got every method that I would want to define this object with. I can define its motor controller, I can define its telemetry, its gearing, motor inverted, idle mode, etc., etc. Here are some of the ones specific to motors in general. This is going to be with control modes, followers, idle, and notice how they're all prefixed with with. This is handy because when you are typing out your code and you type .with, you can use your IntelliSense built in there to see all the different options you have to customize your motor control configs. How do I add a follower motor? If you don't know what a follower motor is, it's like a motor that follows a main one, and it's going to have the same smart motor config as it. So if I had a mechanism and it, say arm, and I have 2 motors on it. Ooh, how do I draw this? There's another motor on it. And then you want it to basically one of these motors, instead of programming it so you have to program the same motor twice, what you can do is set this one as the main motor and then tell this motor to just copy all of its commands and follow it. Follower motors, however, can only be set if these motors are from the same vendor. So if they're both Neos, then you can do it, but if you had a Neo and maybe like a Kraken, then that's not going to be possible because the only alike vendor motors can follow the main one. If you have different motors, or you don't want to use a follower motor method in general, what you could do is once again set these as 2 different motors and have them have their own PID values, their own smart motor configs, so they can share the same set point, but you're not gonna have one smart motor config for both motors, which is a solution to if they're not both from the same vendor. Making a follower motor is very easy. It's .with follower, and then you can create your motor inside here, as well as set its inversion using this B here, B for Boolean. You can add as many follower motors as you want using the .follower or with followers function as many times. So you can have 3 motors, 4 motors, 2 motors, etc. moment of inertia is going to be it's going to help you more accurately simulate your robot behavior under load. This means if I have a arm and it's carrying a frog. Ooh, can I draw a frog? Ooh, this does not look like a frog. Why did I say frog? Okay, he's carrying a little frog, and you want to simulate that. What you got to do is you can use dot with moment of inertia, declare how far away this frog is from its pivotal point. In this case, it's going to be 4 inches, and how much the frog weighs, which is 0.3 pounds. I don't know how heavy frogs usually are, but that seems quite light for a frog for me. But yeah, very simple, and it will definitely help you kind of gauge if your motor is strong enough to carry that load in simulation before you actually test it on the real robot and realize, hey, this kind of doesn't work. Or maybe you shouldn't have frogs on your robot. I think that's why that rule exists. Stator currents and supply currents. Stator current is going to be how much current is being outputted by the motor. When the motor's spinning, it's how much amperage is going out of it. Whereas supply is going to be the opposite of that. It's how much voltage, amps or whatever, is going to be supplied into the motor. So think of this stator as the output, while this is as the input. And what you can do when you set the limit is declare kind of how much the motor is outputting or getting. So if you have a motor and you kind of need it to be a bit more powerful, it needs to do a little bit more, like if you have an active intake, it needs to keep on spinning, then you can set the stator current limit to be higher. While if you're noticing your motor isn't getting enough voltage and it's often underperforming, then what you can do is set the supply limit to be higher so it's able to get more volts out of its battery. But when you're messing around with voltage, you gotta be aware of something called voltage sag. When you have a robot and you have all your mechanisms operating, you're drawing away from its battery. You're taking away from the available bus voltage, which means the voltage of the robots that's available is going to drop. It's going to drop and cause a little bit of a performance drop as well. And not just drop, but also vary, and depending on how much bus voltage is available, it could vary on how the robot actually performs. This is not ideal because when you have a robot, you want it to be kind of accurate, very much the same every single time. To fix this, we can create something called we can have voltage compensation with this method here. Very easy. Voltage compensation, what it does is that it sets a constant, it keeps the output voltage constant despite the fact that there are changes in the bus voltage. Although, even if voltage compensation can help you make sure your voltage sag is irrelevant and has your mechanisms be still accurate, it does not help if you're not having just enough voltage in your robot or in your mechanism in general. This is if you are kind of feeling like you're running out of voltage, this is something called actuator saturation. Actuator saturation kind of looks something like this. You're going to have your mechanism is doing 100% of its total output, yet it's still kind of lagging behind. It's still not reaching its set point, or it's even oscillating, which can be easily confused for PID values. But if you looked at the voltage output of reading on the robot, you're going to realize this is actuator saturation. This can cause your control gains to be kind of too aggressive, and your control algorithm is going to try to move the mechanism faster than it's actually capable of going, which can be pretty dangerous. And in this case, the motor mechanism will be saturated and will behave as if the control gains are smaller than what they are. This can adversely affect the control response, i.e. just not being ideal. When you encounter actuator saturation, you got two ways to doing it. You can either modify your mechanism gearing, or you can power it with a bigger motor. This method is a fun one, function method. You have temperature cutoff, and this is only available with Spark Maxes and Spark Flexes, unfortunately, but they are very useful. This is a very useful one because when your temperature is at a certain limit, what it does is your motor can set the voltage to 0 in the closed loop, and it could help you save your motor from overheating or burning out. However, a lot of vendors don't support this yet, so when you do put this method in, make sure you read your error messages carefully and simulate your robot to make sure that this is functional. Ramp rates and proper control. In general, not recommended. They're often kind of like band-aid solutions to structural problems. You kind of want to keep these whatever to default and try not to change them throughout the season. Ramp rates slow down your control input, and they can be detrimental to the speed of your motors and by proxy your mechanism. Instead of using ramp rates, you should use stator currents and motion profiles like trapezoid profiles or exponential profiles. This can help enhance your PID response as well as your mechanism speed. You got two types of ramp rates. You got open ramp rate here, and you got closed loop right here. The open loop is when you apply is applied when you control your motor via voltage or duty cycle, and this can skew the input to be spread over X seconds. So remember in the past, if you go up, we had our set voltage and set duty cycle methods. These don't have any kind of set point or PID kind of control that you can measure where it's going. It doesn't have a goal it's going towards. You're kind of putting in how much input it has while not really thinking about the consequences or the output. This is kind of different. This is the opposite to closed loop, where you're controlling your motor via set points and set points with closed loops, also known as PID. And this can interpolate your set point to X seconds. So basically, you're in a closed loop system. You are controlling it via what you want it to do. So with a closed loop, you can say go to a certain height or go this fast. Whereas in an open loop, you're saying, hey, I'm going to give you 5 volts, or I'm going to set you to a power of 0.5. Perform at half of your total power, right? So that's the difference between you two. When you're deciding which one to use, do consider them carefully. Although I do recommend closed loops as a personal opinion, because I'm pretty sure they are better because you get to have more control over your motor mechanisms. Idle modes. Idle modes are what they do when they're at 0 power. There are two types of idle modes. Brake mode is when the motor output doesn't move at 0 power, and so it shorts the wires together and try to hold it in place. It's going to be harder to move, but it's not going to be mechanically locked, so you can spin the motor pretty easily, or you can overcome it with high torque. You can probably do it with your bare hands. Coast mode is going to be the motor's braking is not engaged at 0 power. It is very loosey-goosey, and you can move it very well. It's useful in cases where you're moving a mechanism a lot with your own hands, and you don't want it to be in brake mode because you're constantly moving it, or maybe you want to do brake mode because you have a drivetrain and your wheels are suddenly going super totally out of control, and then you had to press your emergency stop on your robot. Well, if it was in coast mode, the robot would go whew and break someone's legs. Whereas if it was in brake mode, the motors would have a little bit more security to actually slow down and stop the robot from actually hurting anyone. And when I'm at 0 power, I want a nap. That was a bad joke. Encoders. Magnetic encoders, through bores, relative, and absolute are the 4 main types of encoders that you're going to be talking about in FRC. Magnetic ones use sensors to measure a rotation of dipole magnets, and they must be placed at the end of the shaft. Through bores is going to be attached directly to the rotational shaft and can be anywhere along the sensor. Relative is going to be different from these two, as they are already built into brushless motors, right here, brushless, and they are unable to get the position of power on and start at 0 internal motor controller. Okay, that's a lot of jargon. I'm going to try to digest that. Okay. So what it's saying is that these are internal motor encoders, and when you power the robot on, it's gonna by default set the angle to 0. It doesn't actually know where the 0 position is on startup. It's basing it on where you set the arm. So if you have an arm and you have it start at 45 degrees, it's going to assume that this here is the 0 degree mark, which obviously when you want to maybe say, hey, move up 45 degrees, or move up to 45 degrees, which is this position, the arm is going to assume this directly here upwards is 45 degrees, which is obviously not. What we want to do is have our 0 degree position be parallel to the ground. How can we do this? Well, if we know for a fact that this arm starts at the exact same spot every single time via maybe a hard stop, or it's just mechanically sound like that, I don't think that's possible, but hard stop is the way to go. What you can do is set the starting position in YAMS using with starting position. And what it does is it's going to know that, hey, I'm not starting at 0 degrees, I'm starting at 45. And it can subtract from that number to assume, like, from 45, and it's going to assume minus 45 degrees is actually where the 0 degrees is. This, however, is not a great solution if your arm doesn't have a hard stop that starts with, or you don't know what this angle is. How can you fix this? Well, have a absolute encoder on your arm. Absolute encoders know where the angle of the arm is even when the robot is powered on or off. And so when you are turning the robot on and off, this angle, whether the arm is here or here or here, it accurately knows where the 0 position is. And what you can do is, if your 0 degrees is not actually where you want it to be, like say maybe your 0 degrees is 45 degrees off, what you can do is set that offset into YAMS again with an external encoder, set an external encoder offset to 45. And what that does is that now when you turn the robot on and off, it knows for sure that this angle here is 0 degrees, and it will let you have more accurate control over the angle and set points of your arm. This one is one of the most important slides on here. It is going to be all about your gearing. So your gearing is what helps you kind of know where your mechanism is, whether it's in degrees or it's in distance. Angles or in distance. So when your motor is trying to calculate what angle it's at, or how many rotations or what degrees it's at, it's gonna be using anything. It's gonna be interacting with the router, right? The sensor is going to be calculating all of that via the router, how much it has already spun. Your mechanism is going to be attached here. And then when you're dealing with your elevator or anything with the distance or speed, like if you're using miles per hour or meters per second, you're going to need to know your measurement. And this is going to be like the circumference of your sprockets or your gears, or maybe the diameter and radius of them. Speaking of which, what is your gearing? Your gearing is going to be the gear ratio between in and out. Ooh, fancy handwriting. And that is usually expressed in rotations, including sprockets and gearboxes. So, up here, if you have a bunch of gears attached to your, before you go to your mechanism, you want to make sure you consider that within your gear ratio. We try to make it super easy to define, so when you need to change it throughout the season, you don't have to calculate a new gear ratio every single time. You can set your gearing with many different ways. This is just a few. You can do with gearing, so just straight up put the number in. You can hand calculate that. Or you can do with gearing and then create a new mechanism gearing where you can create a gearbox, and in there, from reduction stages, you can set each stage of that gearbox. You have a 4 and a 5, and a 3, 4, and 5. And that's the easy way to do so. Or maybe you want to show your gearboxes and your sprockets, and so you can have the stages or the gear ratio of your gearbox in here, and then also write the stages or the gearbox stages of your sprockets in here, gear ratios. Or even simpler, you can just use from stages, and then you write your gear ratios in here. So this one's a 9-to-1 and a 3-to-1. Right? So this would take 9 input spins before it has 1 output spin. There's also one more way I would like to show you, and it's the one I used in my tutorial series. It's going to be, you're going to do with gearing, new mechanism gearing, and then you create a new gearbox. And what you're going to do is create a string array where you can put all the stages you want. So I can add another stage in here, and I can say this is a 5-to-1. I don't know if that one exists. I think they do, yeah. Although, when you're doing, once again, when I was talking up here, this is your measurement, and you're trying to figure out anything related to distance or velocity, you're going to need to declare your measurement. And it's going to be declared using either mechanism circumference or with wheel diameter, wheel radius. And they're going to be treated into the calculations for maybe you're getting your measurements in meters or meters per second, because it's calculating the circumference of that. If you try to maybe do something with meters or meters per second, or you may use these get methods, and you're going to see, and you're not having these methods in your smart motor config, it's going to crash, because how can you accurately prove how far your mechanism has moved if you do not know how much one spin moves the robot or moves the mechanism? Encoder wrapping and continuous wrapping. So this is mainly targeted to any mechanism that has continuous infinite rotation. So this could be like a turret that spins 360 degrees, like this. Whew. Or maybe you have a arm that can also go 360 degrees, and you have I think it's a slip bracket, or I don't know, it's one of those things that allow it to spin forever and ever. Or maybe a swerve wheel that needs to be able to spin in all directions, and you want to make sure you can still allow it to have this freedom of rotation while also have it position or know what angle it's at. This is where encoder wrapping comes in, because every time you spin 360 degrees, when you get to 360 and then go after that 361, you don't want that to be 361, because this would be more useful to know that this is 0 or 1 instead of a large number, because every time you spin this, you don't want this angle to always be huge, like this will be 720, and then this one here would be another big number 360 plus that. You want this to always be the 0 position. You always want this to be 180. You want these angles to always be fixed in a way. And so that's what continuous wrapping is. It will tell the PID controller that the sensor wrapped around its max to the min. And so you have valid options being negative 0.5 to 0.5, negative 1 to 0, and then 0 to 1. 0.5 is going to represent 180, and then 1 is going to represent 360. So if I have my circle here, and I have my 0, my 180, and I spin this way, if I had a wrapping of 0.5, or this one right here, and I go right here at 170, I'm go right at 180, and then I go to 181, what's going to happen is that it's going to wrap around and it's going to go negative. And so this then becomes negative 179 at the very tip right before 0. And so I spin all the way here. But notice once I get to negative 179 and then try to go to 0 degrees, it's going to wrap around and be at 0. That is because of these parentheses right here, fun bit from algebra, and which basically states that it will never reach this max point. If I had a 360 rotation wrapping, continuous wrapping, it could either be this or this. This is just depending on if you want negative or positive being clockwise or counterclockwise. If I had that, and let's say I had 360, I can go all the way here. So this would be 1, 2, 3, 90, 180, and I go all the way here to 364. Or wait, no, that doesn't make 359. If I go to 359 right here, it's going to be still positive. But once I exceed to 0, it's going to go right back to 0, and it's going to wrap and cycle around again. So that's useful. You can set it with continuous wrapping right here, and then set your rotation maximum and mins. Let's see. Okay. We got 2 more slides left. This one is important. It's going to be your soft limits versus your hard limits. Your soft limit is going to measure how far a mechanism has moved digitally and does not allow motors to rotate past its sensor value. What this means is that the sensor is going to read where the mechanism is at all times, and it's going to make sure that it is within the bounds that you set. So maybe you set your soft limits to 0 degrees and 90 degrees. It will always try to make sure it never goes past that. However, since it's using a sensor value, it's software wise, it depends on a couple things. It requires that your encoder is set up properly and is undamaged, and it will also not prevent the mechanism from stopping before its soft limit if the mechanism just sucks in general. Like maybe it's an arm that's too heavy for its motor, it will just slump down and exceed that soft limit. This is kind of where hard limits exist. Hard limits can be a physical button that stop that motor from being pressed. So if your encoder value is kind of off, this can be placed at the end of the mechanism, and it can try to command the motor to stop at some point. And this hard limits are after the mechanism can have inertia and move past the hard limit after the motor is commanded to stop. This is also affected in simulation, as the simulation will not simulate anything past its hard limit, and it is only supported on mechanisms. So when I set my hard limit and soft limit in my code, let's see, I go back in here to my ARM subsystem, and I look at my hard and soft limits. I usually have my hard limits be a wider range than my soft limits, because when I'm simulating my robot, I want to be able to actually see when my soft limit is being exceeded due to maybe a command that's running wrong or whatever bug it is. And so I usually set my hard limits a little bit wider than my soft limits, and that way in sim I can see, hey, this arm is drooping down or this is just going past its limit, and I can debug that through simulation. Last thing I want to talk about is hard stop. Hard stop is going to be nothing you actually program. It's going to be physically preventing the mechanism from moving past any limit. This can be a bumper or some kind of wall that stops the mechanism from exceeding this point. Usually it's a last minute, or not last minute, it's a worst case scenario thing. And so if something goes wrong, the motors will be stopped from moving past those limits. So recommended you get hard stops on your mechanisms, especially arms. And to program a soft limit or hard limit, or you say with soft limit or hard limit, the degree range, your minimum, and then your maximum. Be careful to make sure your hard limit is either the same as your soft limit or greater. The range is greater than that, because you don't want this to be smaller than this, and the robot code is going to get really confused. This is going to be our last slide I want to talk about. It's going to be our closed loop in our smart motor controller config. It's going to be this one up here, and you're going to notice there's two different types. There's your normal one, and this is your sim closed control loop controller. This is going to be your feedback control, which some of you know better as PID constants. This PID helps you correct your margin of error on your mechanism, and it allows for smoother mechanism and also be more accurate in reaching its set points. This is your P, your I, and your D. P is going to be trying to get to a position. D is going to be decreasing its speed while trying to get to that position once it gets close to that position. And then I is going to be increasing its speed when it's far away from that speed or from that set point. And then all three of these in tandem will help you control your mechanism better. For YAMS, you can define them with the with closed loop controller, and it's way better documented in WP iLib. And so I recommend checking those docs out. But YAMS also will have another video going more further in depth into these concepts. One thing I would also like to talk about is going to be the fact that you can easily add motion profiles controllers like this. Here is an exponential profile controller, and then you can look in the API, you can see where to configure all the PID values as well as all of these right here. But this is going to be the end of today's video. In the next video, I'm going to be talking about the feedback, feed forward, and as well as all the different profiles that is provided by YAMS and more. And I'm going to be talking about what does this mean and how can you use these profiles to enhance your robot. If you learned something new today, I hope you like the video, subscribe, leave a comment, and yeah, have a good day.